Okay, we'll pick up where we left off with some factoring, and a lot of times people see a trinomial and they immediately start thinking of the hard factoring, which would be, treating it like a quadratic. But the first thing, of course, we always want to look for is can we factor out a monomial? And I note that 6, 12, 144, 6 divides each of these, and everything has a factor of n in it, each of the terms. So I can factor out a 6 and an n to begin with, which of course leaves me with n squared minus 2n. And then 6 into 144, of course we could do this on a calculator, but if 144 we recognize is 12 times 12, that's 6 times 2 times 12, or 6 times 24. This is minus 24. And now we can try to handle that quadratic, and I'd be looking for factors of negative 24 that add up to be negative 2. And of course that would be negative 6 and positive 4. So this factors as 6n, n minus 6, and n plus 4. And at that time we are done. We're not solving this. There is no equal to. I'm not going to say that n is 6 and n is negative 4 and n is 0. It's just a factor problem. Okay, number 13. Factor completely. Okay, we may actually spend a full day on this. I think it's just such a good, valuable tool. But hopefully everybody's kind of on page of what I'm doing here. To factor when the quadratic, when the lead coefficient is not 1, we can take the product of the outsides, 2 times 28, positive 56, find two numbers that multiply to be positive 56 and add up to be negative 15. Of course, if they multiply to be a positive and add up to be a negative, they must both be negatives. In this case, 7 and 8 get the job done. Now, a common mistake at this time when people are just learning this process is to say, oh, well then it's n minus 8 times, or n minus 7 times n minus 8. But of course, n times n doesn't give us 2n squared, and minus 8 times minus 7 doesn't give us plus 28. That's not it. What we need to do is set the outside product, outside FOIL, first outsides, insides last, the outside product to be either negative 7 or negative 8n. I'm going to choose negative 7n. If I get a prime number, I like using it as one of my magic numbers. So I need two numbers that multiply to be 1, or multiply to be 7. My only choice is either 1 from here and 7 from there, or 7 from here and 1 from there. Well, of course, it's 1 from the ends and steal a 7 from the 28. And to make that negative 7n, this is a minus. So now we got it made. First term times first term equals first term. So n times 2n is 2n squared. And last term times last term has to equal last term. So negative 7 times negative 4 is positive 28. And here's a real quick check in this process. We've already used our magic number negative 7, and the negative 8 pops up on our inside product. So there is our factoring. Again, that may be something that we take a further look at, maybe on on a day like on a Friday after a Thursday test. Number 14. Okay, real simple here, but this is a process when we're working with functions that end up causing some people some problems down the road. We're supposed to find f of negative 3, and when I teach this to Algebra 1 students, if it's the first time they see it, I always have them write out what's happening in f of x, and they would, for this case, say f is a factory that takes things, and I like the use of the word things here. It takes that thing, squares it, and adds 1. So f is going to take negative 3, square it, and add 1. And of course we get 9 plus 1, 10. And I don't think anybody would miss that. But I've seen in even at honors pre-calculus level that some people have missed some when the thing we're taking is a little bit more complicated than just -3. And that's my segue into number 15. So many times I will see this common error. In this problem, I would see something like, well, if p of x is 4x minus 5, what's p of x minus 1? Well, it's 4x minus 5 minus 1, or 4x minus 6. But you don't understand functions. What you just found really here was p of x minus 1. So again, to repeat what we just talked about on 14, p is a factory that takes things, whatever the thing is, it doesn't care, multiplies it by 4 and subtracts 5. The thing just happens to be x minus 1. So p of x minus 1 is going to take that x minus 1, drive it into our Midas muffler shop, where in the Midas muffler shop, all that's hanging on the walls is 4, multiplication, subtraction, and a 5. And what we're supposed to do in that Midas muffler shop is attach 4 to the thing with multiplication and then subtract 5. So it's 4 times the thing minus 5, or 4x minus 4 minus 5, 4x minus 9. Okay, now, you may have some really sophisticated ways to go ahead and graph this quadratic, and that would be great. You could complete the square, find the vertex that way. You may have some memory. All we're intending right here on this is just do what I'm going to refer to as freshman graphing. Start picking some values and plot them until we get a good idea what this looks like. You have the advantage of knowing this thing is going to be a parabola because it's quadratic. But we could just do our old freshman graphing t-charting, and for instance pick 0 for x, and we get 0 squared minus 4 times 0, 0 minus 0 plus 6, 6. And we'll just continue in that fashion. When I put in 1, I get 1 minus 4 times 1 plus 6, or 7 minus 4, 3. So 1 gets me up to 3. 2, I'll write it down here. I get 2 squared 4 minus 4 times 2, 8, plus 6, or 10 minus 8, 2. So my growth, or the amount it's shrinking, is slowing down, and that's good. 3, that would be 3 squared 9 minus 4 times 3, 12, plus 6, or 15 minus 12, 3. And at that point, we know we've got it because we know this thing is a parabola. So we've found our symmetry line, thus found our vertex, and therefore we know we have a point over here. Never looks like a V, a parabola. It's always flat coming out, curves up, flat coming out, and curves up and through. So that's all we're looking. We'll talk about much more sophisticated methods. In fact, on day 1 in this course, we would have said, well, we know for sure this thing's starting at 6. We know for sure it's going down as it goes through that. So we would have known that much to begin with. We also would know it ends up acting like a positive parabola, so we would know that the cupping is in this shape. Now, we don't know necessarily how far down it goes, but we'd have all of that information just from that day 1 lecture. Number 17. Okay, here's a case where I would not freshman graph this because you guys know this is in slope-intercept form, y equals mx plus b. So in this case, we're going to start at -4. And I always talk about this being, once we're in slope-intercept form, I talk about it being like corn growing. So it's like, where do we plant the corn? How fast does it grow? In this case, we plant the corn down 4, and we expect it to grow 5 inches every 2 days. So up 5, over 2, almost room to do that again. Up 5, over 2, do the best I can here. And we have a line like that. Our second line, our corn starts 4 inches tall, and this corn is actually shrinking 3 inches every 2 days. So down 1, 2, 3 over 2, and that's what we're looking for right there. That gives us our intersection, or our solution of the system is right 2, up 1. Very simple. How could this problem be a little bit tougher? Well, of course, we don't have to get the equations in slope-intercept form, and we would have to work with those a little bit. So I'm going to take this first equation, 3x plus 4y equals 8, and solve for y. I subtract 3x on both sides. 3x joins a plus 8, and I divide 4 every term. And now I know that we plant this corn up 2, and it shrinks 3 inches every 4 days. Or if we go backwards in time, it would have grown 3 inches from 4 days ago. So we have a line like this. Now let's take a look at the second one. I could have probably done this with the first, but the second one's so nice. 1 and 2 both divide into 6. How about if I just did a quick look at the intercepts? For instance, if x equals 0. If x equals 0, negative 2y is 6, making y negative 3. If y is 0, then I just get x equals 6. So I have a point over here at 6, 0, and as this goes up through there, it sure looks like the intersection might be 4, 1. Let's give that some thought. Here I go up 3 over 6, which is up 1 over 2. So I could go up 1 over 2, up 1 over 2. Sure enough, there's our intersection at 4, negative 1. So if there's an option for you, of course, we could have gone slope-intercept form. Number 19, write the slope-intercept form, y equals mx plus b. And I know a lot of you would probably just work in slope-intercept form here. For instance, you would say y is 2 when the slope is 1/4 times x is negative 4 plus b, solve for b, and there's nothing wrong with that. However, if I'm given a point and a slope, I just start in point-slope form. Y minus the y coordinate equals slope times x minus the x coordinate. Or y minus 2 equals 1/4 x plus 1. Add 2 to both sides. Y is 1/4 x plus 3. Take your pick on that. If you are a devotee to slope-intercept form, that's fine. All I'm going to say is if this had just said, if the directions this was, write the equation of a line through the given point with the given slope, you would be done right here. Whereas if you do the slope-intercept form, you still have some extra steps. So give me a point, give me a slope. That's what point-slope form's for. Number 20. So again, slope-intercept form. We've got 2, 4, slope-intercept form. We're going to wind up in y equals mx plus b. To get the equation of a line, we need a point, we need a slope. But if I'm given 2 points, I'm given the slope. The slope is change of y's. It's amazing to me how many times an honors pre-calculus student, level student, will miss finding slopes. Over change of x, 2 minus 0 is 5 halves. And now I could go point slope form, and if I was going to go point slope form, I could use either point. I would probably choose this point. However, real quick picture, where is 0, 1, or 0, negative 1 right here? That is our y-intercept. So our equation is y equals 5 halves x minus 1. Simple. Okay, 21, dreaded story problem here. If I'm given a percent of problem, I'm going to set this up in a chart. I used to fight charts. Percent of, we're talking about a solution here, is percent of solution is, in this case, a saline solution, 90%, I believe that's a salt solution, is salt. So we start with, I'll call this 4 fluid ounces A. And we start with a 90%, 0.90, of means times solution. How much solution do we have? 4 ounces is equals the amount of salt in there. Well, zero point 0.9 times 4, 3.6. And then we mix in 2 fluid ounces, I'll call that B, of 72% saline solution. How much of that? 2. Well, that ends up with 1.44. And then the question is, what is the concentration of the mixture? Well, how much salt do I actually end up with when I mix that? 5.04. How much solution do I end up with? 8. What's our final percent? P. So we end up with P times 8 equals 5.04, or P equals 5.04 divided by 8. And of course, we have to change that into a percent, but I will leave that for you with the calculators. Okay, number 22. Find the product, superfoil. We should be very, very good at this. You can organize this in a different fashion, but I will just typically take the first times each of these terms, so I get 24n to the third, 6n times negative 8, negative 48n squared, minus 6n. And then the second term, minus 8 times 4n squared, minus 32n squared, plus 64n plus 8. And then just group terms. That's my only cube. Minus 48 minus 32 minus 80 n squareds, minus 6 plus 64 plus 58 n's, and just a plus 8. Simple, just a little bit of work and organization shouldn't cause any problems. And 23. I don't have to look very far. The first thing that draws my attention is this. We got distance, rate, time problem, and there's typically 3 types of these. There's one where you've got 2 different entities going in 2 different directions and you deal with the total distance. There's one where 2 are going in the same direction and then you end up figuring out the difference between the 2, so it's a subtraction problem. And then you've got others where someone starts out at different time as somebody else, different speeds, and you wonder how long does it take for this to catch up. No matter what it is, I'm going to set this up as rate times time equals distance, and we are dealing with Julio. And Julio left school and drove toward the desert at an average speed of 60 kilometers per hour. Sarah Wong left 1 hour later and drove in the same direction, but going 80. Find the number of hours Julio drove before Sarah Wong caught up. But Julio left an hour earlier. So when did Julio leave? I could put T here, but I'm just going to use X. And here's where the most common mistake is made in these. We just say, well, it's X minus 1, X plus 1. It's almost sometimes feels like students are just guessing at this. Who has been on the road longer, Julio or Sarah Wong? If Sarah Wong left 1 hour later, Julio has been out there longer. This is the big number. So this must be X minus 1. Well, rate times time equals distance, 60x. Rate times time equals distance, 80 times x minus 1. And what are we looking for here? Add them, subtract them, set them equal. We want to know when Sarah Wong catches up when this distance equals this distance. So 60x is 80 times x minus 1. And now we have to be really careful because as algebra-trained chimpanzees, we are used to coming up with x as an answer, but is x actually the answer here? X will give us how long Julio's been out there, but the question could very easily have stated, how long will it take Sarah Wong to catch up from when Sarah Wong leaves? But it says, find the number of hours Julio drove. So X will be our answer, dot, dot, dot. Solve for X, and that would be unit of hours. So with these two-part videos, everything that could be on your quiz, in this case in 2012, or the fall of 2012, in this case the quiz is going to be on Tuesday. Everything that could be there should be represented in one of these quizzes. Make certain by Tuesday that you are completely comfortable with all of this. Thanks for watching. Hope that was helpful, and stay tuned.